For more explanation, let us start from two charges. Let's say we have charge 1, which is Q1, and charge 2, which is Q2. They are separated by a distance of R12. Let's say this distance is R12. So if you are asked to find the electric potential energy, 12, which is equal to 1 over 4 pi epsilon naught first charge Q1 multiplied by the second charge Q2 divided by the distance between them R12. This is for two charges. If you have three charges, like first charge Q1, second charge Q2, and the third charge, let's say Q3. So to assemble this, let's say the distance between these two is R12. This is charge 2, and the distance between these two is R23, and the distance between these two charges is R13. So the electric potential energy for assembling these three charges and the vertices of this triangle will be equal to, first we need to find first electric potential 1 and 2 is equal to 1 over 4 pi epsilon naught Q1 multiplied by Q2 over R12, and in order to find the electric potential when 1 and 3 is equal to 1 over 4 pi epsilon naught Q1 Q3 over R13, and then between 2 and 3 we have 3 electric potential energy 3 over 4 pi epsilon naught Q1 and Q3. No, this is 3. This is 2. This is 3, 2 and 3, which is R23. Therefore, in final, the total electric potential energy is equal to, that is 1, 2 plus 1, 3 plus 2, 3. And this will be the total electric potential energy, the sum of these two. Then the common value is 1 over 4 pi epsilon naught. 1 over 4 pi epsilon naught is common. Then inside we have Q1 Q2 over R12 plus Q1 Q3 over R13 plus Q2 Q3 over R23. So this is how we find the total electric potential energy when in assembling these three charges. Consider four charges: charge 1, second charge, charge 2, and they are separated by R12, and this is charge 2, and next we have another charge which is Q3, and this one separated by R13, and let's say we have another charge which is Q4 separated by, this is R24, and this is R34. So in order to find the total electric potential energy, we start from the first one. Between 1 and 2 we have 1 over 4 pi epsilon naught Q1 Q2 over the distance between these two charges, which is R12, and then between 1 and 3, which is 1 over 4 pi epsilon naught Q1 Q3 over R13, and then we need to see the other values, which is 1 and 4, which is equal to 1 over 4 pi epsilon naught Q1 Q4 over R14, and then between 2 and 4, which is equal to 1 over 4 pi epsilon naught Q2 Q4 over R24, between 2 and 3, which is 3 1 over 4 pi epsilon naught Q2 Q3 over R23. Okay, and the last one is between 3 and 4. So which is 3, 4, which is equal to 1 over 4 pi epsilon naught Q3 Q4 over R3, 4. So after this, we need to find the total. The total will be equal to the sum of individual one. Therefore, we have to write like this: total is equal to between 1 and 2, the electric potential energy 1 and 2 plus 1 and 3 plus 1 and 4 plus 2 and 3 plus 2 and 4 plus 3 and 4. So when you add them together, we will get common value. The common value is 1 over 4 pi epsilon naught for each. Therefore, for this one, we have Q1 and Q2 over R12 plus for this one, it is Q1, Q3 over R13 plus for this one, it is Q1, Q4 over R14, then plus between this is Q2, Q3 over R23 plus between these two we have Q2, Q4 over R24 plus Q3, Q4 over R34. So with this, it's possible to find the total electric potential energy to assemble. Example, find the electric potential energy in assembling 4 charges at the vertices of a square of side 1 centimeter. This is the vertices of square, and the distance between these 2 charges is 1.0 centimeter. Start each charge from infinity as shown in the figure. So we bring them together to form this square. So we have these different types of charge. First charge 5 microcoulomb, 4 microcoulomb, 3, 2, 1. So as we have seen in the last session, so the potential energy is equal to between the first charge, the second charge, the first charge maybe with the third, and the fourth, and so on. It continues like that. So total potential energy is the individual one. First one is U12, the second one U13, U14, U3, U24, and U34. So 1 over 4 pi epsilon naught is common. Then we substitute these charges. So 5 times 2, 5 times 2, the distance is 1 centimeter. So when you change into meter, it becomes, so this is microcoulomb and this one is microcoulomb. So 5 multiplied 2, and we have here 6 and minus 6, which is minus 12. So this is 5 with 4, 5 with 4, and 10 raised to minus 2, and 5 with 3, 5 with 3, and the distance is this one, the diagonal, which is square root of the 1 centimeter, 1 centimeter 10 raised to, which is square root of 2 centimeter. So we have to change into a meter. Then 4 with 3, and 4 with 2, and 3 with 2. So finally we'll get 57.8 joule. Okay, another example. If you have a 12-volt motorcycle battery that moves this much, 5,000 coulomb of charge, and 12-volt car battery that moves 60,000 coulomb of charge, how much energy does each deliver? So we know that V is equal to the electric potential energy by Q, multiply those side by Q, and finally you get the electric potential energy Q will be. So first we start for motorcycle battery. The voltage is 12 volt, Q is V is 12 volt, and the charge it can move is 5,000 coulomb. So we multiply 12 volt is 5,000 coulomb, it becomes 60,000 joule. And the second one is we have 12 volt battery multiplied by 60,000 coulomb, and it becomes 720,000 joule, which is 0.7 gigajoule. Current I, which is equal to the change in charge, the change in time. So change in charge you have to find first, or it can be given in terms of where I is equal to derivation of Q with respect to time. For example, if Q is given as a function of time, just like this one, 2t square plus 3t plus certain value like 4. So if you are asked to find the current I at t is equal to, let's say, 2 seconds. So in this case, first you need to find I as a function of time. I as a function of time is equal to derivation of this cube as a function of time with respect to time. Then it will be equal to, this will be equal to the derivation of this one, derivation of by dt of 2t square plus 3t plus 4, and this will be equal to 4t plus 1 times 3 is 3 plus 0, so 4t plus 3, therefore I of t is equal to 4t plus 3. So current depends upon time, therefore there is a change in current when the time varies. Now the question is, find the current at t is equal to 2 seconds. Now substitute 2 seconds, therefore I at t is equal to 2 seconds, which is equal to 4 multiplied by 2 plus 3. So this will be equal to 8 plus 3 ampere, which is 11 ampere. This is it. Current actually means, consider this is a conductor. So we have this cross-sectional area. So we have a large number of charges that are flowing through this given area. Very large number of charges. So this current implies that it's flow of charges. Flow of charges in a given time. We have to consider the time and the area. So this is the area, and so the time interval should be taken under consideration. So let's say 1 ampere. Let's say 1 ampere. It is 1 coulomb over 1 second. This means there are 6.25 times 10 raised to 18 electrons flow. They are flowing through the area in each second. Through this area, they flow through this area in each second. So this much number of electrons passes through this area, this cross-sectional area, in each second. So in 1 second. So if we have a conductor that carries 1 ampere, which means that in the given cross-sectional area, this much number of electrons passes in each second. We know that 1 electron, which is equal to 1.6 times 10 raised to minus 19 coulomb. 1 electron contains this much coulomb. So here we have 1 ampere means 1 coulomb over 1 second. That's why it becomes this much number of electrons, 6.25 times 10 raised to 18 electrons flow through. So another one here is regarding resistivity. When voltage is applied to a conductor, an electric field is created. The charge in a conductor feel a force due to the electric field. The current J that results depends on the electric field and the properties of the material. Conductivity is an intrinsic property of the material. That is the representation of the conductivity. So another intrinsic property of material is the resistivity, which is 1 over conductivity. Electrical resistivity, the resistivity of material, is a measure of how strongly material opposes the flow of electrical current. Symbol for resistivity is the lowercase Greek letter, which is rho. The resistivity is the reciprocal of electrical conductivity. So we can write resistivity is equal to 1 over the conductivity. Can define resistivity in terms of electric field and the J value. So J is actually current over the area. So when area increases, the J value will decrease. It states that the voltage applied across the end point of a conductor is proportional to the flow of electric current. Mathematically, V is directly proportional to I. V over I is constant, and this constant is called resistance. Okay, in electric potential or electric field exists between two potentials, points from higher potential to lower potential. Recall that the electric potential is defined as the potential energy per charge. So changing Q loses potential energy moving through the potential difference, these two potential difference. So the electric field can be given as the potential difference, or V over L. V over L will be the value of the electric field. But if you want to find the work, force multiplied by L, we know that force is equal to the electric field multiplied by the charge. So therefore, from here we can understand that the electric field is equal to V over L. Substitute here, V over L, L cancelled by L. Finally, work is equal to QV, which is equal to the electric potential energy. The power is the electric potential energy per time. So we know that this is Q times V over T. Q over T is current multiplied by V. Q over T is current, IV. So when we substitute V with I times R, I times R times I, this is I squared plus R. Or if you substitute this one, the current, which is V over R, V times V, V squared over R.